SwayamPrabha. Digital India. Educated India.
So, that means if you now compare the Goldfield contest and this Bruce Pag and Godfrey test, then you are actually arriving at same type of conclusion. Okay, same type of conclusion. So, in Stata, they have a ready-made command to conduct this test, and that is basically I will explain this. So, once you run your original model reg consumption on income, then the command for Bruce, Pag and Godfrey test is head test, and see the value is 5.21, exactly the same value what we have derived. Okay, same value, manually whatever we have calculated, Stata is also reporting the same chi-square value. And what is the probability that the calculated value is greater than the tabulated one? Look at the p value, 0.0224. So, that means if you multiply this by 100, you will get 2.24, which is greater than 1, but less than 5. So, that means it is significant at 5% level. So, you can reject your null hypothesis at 5% level of significance, right, at 5% level of significance. All right. So, this is the Bruce, Pag and Godfrey test, but there are two limitations of this BPG test also. What are those two limitations? Two limitations of BPG test. First of all, this chi-square, what I said, this chi-square, this ESS by 2 is asymptotically follows, here I will write asymptotically follows chi-square distribution. That means this particular test statistic follow the chi-square distribution only in large sample, Also, the sigma square tilde what we got here to adjust your UI hat square, and that is, you see, that is the definition of sigma square from the maximum likelihood method, and maximum likelihood method is applicable when you have a large sample, but here you have only 30 observations. Though these 30 observations may not actually define a large sample. So, that is limitation number 1. Half of ESS asymptotically follow chi-square distribution. That means, this particular test statistic you can derive only when your sample size is large. So, limitations of BPG test. First one is that half of ESS follows asymptotically chi-square distribution. That means this implies this test is applicable only in large sample. Only in large sample. Okay, only in large sample. And second limitation is that in your original model, UI actually follows a normal distribution. So, this test largely depends on the normality assumption of the error term in the original model. So, that means this implies this test largely depends on the normality assumption of UI in the original model. To overcome these two limitations, there is one more test which is called White general heteroscedasticity test. White's general heteroscedasticity, in short I will write HET test. How is this test? Suppose your original model is yi equals to alpha plus beta 1 x 1I plus beta 2 x 2I plus ui. This is your original model. And here what they say, the test is very simple. You estimate this model and then collect ui hat square. And then you regress this ui hat square on lambda 1 x 1I plus lambda 2 x 2I plus lambda 3 x 1I square plus lambda 4 x 2I square plus lambda 5 x 1I x 2I plus epsilon I, and then get, this is step 1, this is step 2, and then from here you get R square. And in step 3, if you multiply this R square, that will follow again x chi-square distribution with degrees of freedom equals to k. This is, let us say, equation 1, this is equation 2, which is also known as auxiliary regression. K equals to total number of explanatory variable in, or I will say the total number of parameters in the auxiliary regression but excluding the intercept. Right. So, that means from the auxiliary regression, alternatively you can check, instead of constructing n multiplied by r square, you can also test lambda 1 equals to lambda 2 equals to dot 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 lambda 5 equals to 0 or not. Let us say this is my null hypothesis. How will you do that? By F statistic. And if lambda 1, lambda 2, lambda 5 all are 0, then sigma square equals to what? That means only lambda 0. So, if this is if this is not rejected, that means sigma square equals to only lambda 0, that means there is no presence of heteroscedasticity. But if H naught is rejected from this auxiliary regression, if you conduct a test, that means ui square, ui hat square actually equals to lambda 0 plus lambda 1, lambda 2, lambda 3. So, that means again I can say that variance of ui is a function of x. So, this is a different type of functional form we have assumed, okay, different type of functional form. Now, why White's test is called general heteroscedasticity test? Why White's test is called general heteroscedasticity test? Can you think of? See the specification of White test. You have ui hat square equals to all the explanatory variable, its square and cross product. If this cross product terms are significantly, they are 0. If you have more number of explanatory variable, you will have more cross product. So, if the cross product terms are 0, so that means if the cross product terms are 0, then it is a pure test of heteroscedasticity. If the cross product terms are not 0, then not 0, then this is a test of heteroscedasticity as well as model misspecification. That is why it is called a general test, because you are testing heteroscedasticity as well as model misspecification. Now, you can take the same data set and again you can manually conduct this White's general heteroscedasticity test, and that you take as an assignment. So, conduct this test at home. Conduct White's test at home. Okay, this is your assignment I am giving. Now, here what I will do, I will just show you how to do it in Stata. So, here I will just show you how to do it in Stata. So, in Stata, once again if you run the original model, reg consumption and then income, after that you have to do IM test White. What is the command I am saying? IM test White, that is the command for White's general heteroscedasticity test. And from there what you can do, what you can see, that chi-square value is 5.33 and the p value is 0.0696, that means it is significant only at 10% level. But once again you have to remember that even the White's general heteroscedasticity test is also a large sample test, which may not be applicable in a small sample in this case, because you have only 30 number of observations. Why this is a large sample test? Because see, in your auxiliary regression, UI hat square is a function of all your explanatory variable, its square and cross product. So, with two explanatory variable, with only two explanatory variable, you are having 5 parameters. So, you can imagine if you have 5, then all the 5 explanatory variable, its square and cross product, that means 5C2 terms cross product times cross product terms would be there. So many explanatory variable will appear in the auxiliary regression, and that will eat up lot of degrees of freedom. Okay? So, that is why you need to have a large sample to conduct this particular test also, right. Okay, now the question is, alright, we have detected the heteroscedasticity, but what is the solution? How will you solve heteroscedasticity problem? So, the solution is Suppose so in your model yi equals to alpha plus beta xi plus ui, and you are saying that sigma square equals to sigma square I. Okay. So, that means variance of ui, instead I will write variance of ui equals to sigma square I. So, there are two cases when sigma square I is known to you, somehow you know the error variance, sigma square I is known to you. So, in that case, if you simply divide this equation, instead of estimating that original equation, you just divide the equation by sigma plus beta xi by sigma I plus ui by sigma I. You divide the equation, okay, and then run OLS in the modified regression. If you run OLS in this modified regression, that is called generalized least square method. Now, the question is, with OLS is not applicable in the original model, how come we are able to apply OLS in the transform model? Because if you calculate the variance of this ui by sigma I, then that is nothing but expectation of ui divided by sigma I square, which is nothing but 1 by sigma square I into expectation of ui square. And what is expectation of ui square? That is also sigma square I equals to 1 by sigma square I into sigma square I equals to 1. So, that means variance is constant in the modified regression, while it was not in the original regression. Now, if you look at the procedure, that means what I am doing in the original regression, in this regression, while doing OLS, we were trying to minimize ui hat square. And here what I am trying to minimize in this generalized model, we are trying to minimize ui divided by sigma I square. So, this method is also known as weighted least square method. where 1 by sigma square is basically the weight, So, that means higher the variance, lower is the weight you are attaching to that particular error term, okay, to that particular error term. Now, how it is different from OLS? How it is different from OLS? This is YI. In OLS, what was happening? So, this was our error term. This is my error term. Suppose this one is U1 and this is U4. So, when you are minimizing summation ui square, that means you are basically minimizing summation u1 square plus u2 square plus un square. So, that means you are attaching same weight for all these error terms, but here in the WLS or weighted least square, what I am doing, I am attaching 1 by sigma as the weight. That means higher, that means when your distance is too far from the predicted line, I will attach only the lower weight. So, weight is inversely proportional to the distance of the error term from this. So, that means higher the value of the error term, lower the weight I am attaching, okay, lower the weight I am attaching to that particular error term, and that should be realistic, that should be justified also, because this error term contributes less towards constructing this regression line. Why should I attach too much weight to this? Why should I attach similar weight to U4 with that of U1? U1, because this is too close to the predicted line. So, that means this is contributing more, this is more important than this error term. Okay? If you put equal weight, then U4 will dominate the summation ui hat square. That should not actually happen, that is the problem of OLS. That is why in WLS I am saying I am attaching weight, and weight is actually inversely proportional to the value of this. Higher the U, lower would be the weight attached to it. That is the logic. Okay? But the question is, this is all right, you can transform the equation when sigma I square is known, but when it is unknown, then what you will do? When sigma I is unknown, sigma I is unknown, we should get White's heteroscedasticity consistent standard error actually, because ultimately your standard error will get affected in presence of heteroscedasticity. So, you have to get this, and this particular standard error, White heteroscedasticity consistent standard error, that is known as robust standard error. Robust standard error. Okay, and nowadays in all the statistical softwares, they routinely compute the robust standard error, which is basically White heteroscedasticity consistent standard error. That means assuming there is a presence of heteroscedasticity, what is the standard error? A large difference between the OLS standard error and this robust standard error indicates that your data is basically suffering from heteroscedasticity problem. And if you go to your data set once again, So, if you run this model reg consumption, then income, after that you have to put a robust command to get robust standard error. Okay, robust standard error. Now, you see the standard error for the income coefficient is 0.0298, and in your original model, if you run simply reg consumption on income, then your standard error is basically 0.0286. So, there is not much of a difference in the standard error. That means presence of heteroscedasticity is not so severe, and that was prominent from the white heteroscedasticity test also, that you can reject the null only at 10% level, right. This is how you can get the robust standard error to solve the heteroscedasticity problem, if at all anything is there, right. Okay. So, with this we are basically closing our discussion on heteroscedasticity. Now, you see we have discussed autocorrelation, we have discussed multicollinearity, and now we have discussed heteroscedasticity. That means we have relaxed only 3 assumptions out of 10 we mentioned in the context of classical linear regression model. That means we assume other 7 assumptions are maintained. Out of those 7 assumptions, there is one more assumption which is also very important, known as, let us say, yi equals to alpha plus beta xi plus ui, where we assume this xi is basically non-stochastic. Stochastic or exogenous. That means covariance of this xi and ui is actually 0. This is not correlated with this error term. But in case covariance between xi and ui is not equals to 0, then that is called xi is endogenous, and it will lead to endogeneity problem. So, this endogeneity problem if you have in your data set, then your OLS method is not applicable. You have to use instrumental variable estimation technique. But this IV technique or instrumental variable estimation technique is beyond the scope of this basic econometrics, the course what we are dealing with, that comes under the next course, which is applied econometrics, right. But you should aware of this problem also. This is also one of the assumption that we maintained in the context of classical linear regression model, that all our explanatory variables, they are exogenous in nature, and that means they are not correlated with the error term. So, with this we are closing our discussion of this module, that means relaxing the assumption of classical linear regression model, autocorrelation, multicollinearity, and heteroscedasticity, detection of the problem, consequences, and the solution we have discussed. Thank you.